This looks good. Okay, so the next topic that we are going to discuss is the polarization of the wave. Okay, polarization. So first of all, we often say that whenever we give the equation or the mathematical construct representation of a wave, we look at expressions that look like this. Let's start from this, for example. H is equal to AY times H0 times e to the power minus j beta z times e to the power j omega t. Okay, so let's call it like this. Let's assume that we have, this is the propagation in space, which should be along the positive z, and this is the time propagation, which is along the positive time. This is how it goes. And then we can ask the question, what is the polarization of this wave? Who can answer this? What is the polarization of this wave, of H? I can ask Leonard. Leonard, since you just stepped in the class, I mean, you wrote your comment. What is the polarization of this wave that is on the board? Okay, anyone who can activate the microphone? Who can answer this?
Professor, I think it's direction of AX.
That is correct.
The electric field.
That's correct, because the polarization, this is defined as the direction of the electric field. Okay? So polarization is what? Polarization, we see it from here. So we see whatever the direction is, how can I say this one? AE, the unit vector along the E, times the amplitude of E. In this case, we also know that wave propagates, so direction of propagation K, it's equal to E cross B or E cross H. So in this case, the propagation is AZ. So here we have AZ, this would be equal to AX cross AY. I think it looks good. So the polarization of this wave, which we have reported here, is the polarization is this AX. Why? Because the electric field associated with this magnetic field has to be in a specific direction so that the wave can propagate in plus Z. That's good. So that's what we have to take track about. Now E, in this case, what is the direction of E? So here I wrote this unit vector along the electric field, but this is AXE. Okay? Okay, let's try this one for a moment. This is the electric field. But the electric field, it can also be written like this. E is not always in the direction of one of the orthogonal directions. It's not always along the x, y, or z. It could be also a projection in the xy plane. It could be at another direction. So we can write this one as EX, AX, plus EY, AY. Okay, so this could be also the polarization of a specific wave. Now, keeping this in mind, we can construct, or we have denoted, determined, or defined specific polarization directions depending on whether these two components are equal or not, or whether these two components are out of phase with respect to each other. Okay. So, for a general description of a wave that looks like this, we have to look at two major components. One, check, let's write it like this, check EX over EY, okay? Check whether they are equal, okay? That's the first thing. The second thing is check the phase, okay? What is the phase between these two waves? So does the component along the x direction decrease at the same rate as the component in the y direction is doing? So if we try to write this one, let's imagine for a moment that this is the x direction, this is the y direction, and then we have the wave which has here, let's denote it like this. This is EX, okay, and this would be the EY. So, so we are given these two quantities, we have the direction, that's fine, but now we have to check what is the ratio between these, and then we have to check what is the phase. How do we check the phase? the phase, we try to determine how much radians are different between when one of the waves is a maximum and the other one is a maximum again. So we check the delay in time of when do they reach the maximum peak with respect to one another. If they both reach the peak at the same time and they become zero at the same time and reach the negative amplitude direction at the same time, we call this in phase, okay? So the phase difference between those, so let's right here, check phase difference. Let me correct this one, okay? Okay, with this general, so what can happen is that for this wave, a little later, probably we can draw it like this. So let's assume that the wave, this is xy, these two components, they would move like this, okay? And like this. So, and the magnitude, it used to be like this long, but it was here, it was here. We see that this one is propagating and things are becoming smaller. It could be one point in time where these move in the opposite direction, and the amplitude of this wave, it would be down here. Okay, this is x and y, and we're trying to denote that the wave is moving out in this direction. So now, based on this, what we are seeing so far, we can determine the first polarization. It would be linear polarization. Linear polarization, we denote this one as LP, and this linear polarization is the following. So we have E, we have EX, we have EY, and they are both in phase. This is what we can call it as linear polarization. So in this case, if we see this drawing here, it looks like they are in phase because they are both amplitude maximum, this EX and EY. A little later they both decrease, a little later they become zero, and they turn, the amplitude becomes in the negative, is pointing in the negative x direction, and the magnitude of EY is pointing in the negative y direction. So this would be a linear polarization. And why do we call this one linear? We call this linear because the electric field, we know how we add x component and y component vectors, right? So the total field, it would be here, at an angle of 45 degrees, okay? If they are equal initially. And then a little later is going to be here, then later is going to be here. So if we add up these EX and EY at each time progression, we have to notice how this tip is changing. Okay, we have to check what is this tip doing. This tip, what it's going to do, is going to move in a line. Okay, it's going to move back and forth. So if you just say γρόσημα τα βεκτόρια φούσας ηλεκτρικά τotale, όταν γρόσημα measure, that color point is going to move a line. It's going to be something like this. Okay, or maybe like this. It's going to preserve a specific angle with respect to the x-axis all the time. So I have a laser pointer from here. I point right to the camera, right to you, and you're going to see this vector moving like this. So this is called linear polarization. Why? Because the electric field vector, which is now, it has a projection on the x-axis and on the y-axis, but they are in phase. So that one, the tip will always follow the similar pattern. In this case, we can write this one as Ex as a function of z and time. So once you see this expression, what is it? This is the instantaneous electric field. So let me write this one. This is instantaneous electric field, and this is equal to the amplitude along the x, C1x, cosine omega t minus beta z plus the Greek sigma. So this would be the Ex, the Ey as a function of z and time. This would be equal to C1y times cosine omega t minus beta z plus the Greek sigma. So if we look at these two components, they are both in phase, and if they are in phase, this would make them linear polarization. Now, this is LP. Probably is almost very intuitive, and it is easy to understand. Now, let's pick up another type of polarization. So we have here linear polarization. We can also define circular polarization. And circular polarization, based also on the word which is carried circular, you might assume that now the tip of the electric field is going to draw a circle. Okay, so you're going to see a circle approaching to you as the wave is moving in this propagation direction. The electric fields, the Ex and Dy, that's going to be like this. But apparently, there is a possible configuration where you'll see it rotating. Okay, and how can this be? This is made possible whenever. So this was polarization. We did linear polarization. Now we're going to see circular polarization. And circular polarization, it is one where the amplitudes are equal. So if we have here C1x and C1y, these two are equal. Let me write it like this. C1x is equal to C1y, but they are out of phase. Okay, so if we try to draw them here, being out of phase, but how much out of phase? This is also very, very important. Out of phase by an angle of pi over 2. This would mean that at one instant, the electric field is going to be maximum, so it's going to be here, and the component along the y-axis, it will be 0. A little later, this is going to be shorter, so let's preserve the amplitude, let's preserve it like this. So a little later, it's going to be, let's make it like this. It's going to be like this. And later on, the magnitude of the electric field, we should be able to find it like in here. So this is going to be a maximum, and this is going to be 0. So this would be the circular polarization. We're going to find that this C1x would be equal to C1y, but they are out of phase. Okay, they are never maximum at the same time, and the delay is pi over 2. What does this pi over 2 mean? This means that before, actually, we know that the full cycle is whenever we complete 2 pi, right? So completing 2 pi in phase, in a Hapsian phasora, pi over 2 is 1/4. So this is pi over 2. This will make a pi. This is 3 pi over 2, and this will be 2 pi. So apparently, this is what our pi over 2 means in this case. And then these components, we can write them as follows. So we can say that Ex, also we can compare with what we wrote here. We can have E1x or Ex, sorry, the electric field in the x direction. This would be C1 cosine omega t minus beta z, and the Ey would be equal to C1 cosine omega t minus beta z plus pi over 2. Okay, so if we look at so here we just have any angle psi or sigma, whatever this is in Greek. I always have a good student who knows Greek alphabet very, very well, much better than me. And often they correct me, Professor, that's not sigma, that's eta. I say, okay, sorry. So,
Profesora, eu le zovem X në greqisht. Le zovem X.
Kristina?
Po, le zovem X ajo në greqisht.
Kjo është X?
Po.
Okay, thanks. Po të pak nuk kjo është omega, edhe kjo është beta, këte i kam rregull,
Ato janë, ato po.
Ato i kemi rregull, okay. What about this one? Is this eta?
Po, I thon ita, në fakt, po kënë shqip eta.
Okay, eta. Yeah, eta is also in English. I call it eta. I could pick this up. So this is X. Okay. Okay. Thanks for the correction, Christina. And then, because we have some students that come from some colleges that are also in Tirana, but we have also students that have studied in Greece, so they know It would be good to have also some students that have know a little bit of Latin, but Latin is even a lost language. Only medical fields know it. But let's move forward again with a little note. Here we notice that we have this delay in, let's call it, in phase between these two components. But now, if we have, there is also one little trick here. This can be plus pi over 2. It can also be minus pi over 2. So it doesn't matter. But what would the plus and the minus sign change is that we would have a right hand circularly polarized right, or a left, for example, or a left hand circularly polarized light. Now the right hand circularly polarized light, we can write it like this. Maybe we can draw it like in here. Let's try to imagine which one would be the right hand circularly polarized. The right hand circularly polarized would be one that, if we take the right hand this way, the electric field vector, it should move in this direction. Okay. So if that one is going to move in that direction, then the angle, this should be minus. So minus, so this would be right hand circularly polarized. And if it is a plus, this would be left hand SCP. Okay? So you can read over there in the plus red, the red plus is this, the blue negative is this. But let me try to check this one once again, if I am correct or not. Probably, I think I am right. Okay, because at t equal to 0, let's wait for a second. So let's fix everything, and as time is progressing, if we have a minus sign here, the E will be delayed. Yes, and as EX will be decreased, the EY will increase with time. Okay. Yes, I think this is right hand circularly polarized. And the other one is the left hand. Now, I can also, as we're doing these, it looks like when we write down the electric field component, probably it's good if we take this out. You know that the propagation, we know the following. We know that the wave propagation k is always E cross H, right? But now the E would be equal, what would the E be here? E would be something like this. It would be C1 plus C2 plus a J, okay? We put a J here because a delay of pi over 2, it's a complex number J, which will come in. Because when J or I, okay, square root of minus 1, so this I or J, we know that this is equal to e to the power J pi over 2, okay? Or maybe better if we write it like this, exponential of J times pi over 2. At the same time, minus 1 is equal to what? Minus 1 is equal to I squared. So this I squared is going to be equal to exponential of J pi over 2 all squared. Or we can write it like this, J pi over 2 squared. This is going to be E J pi. And also, for example, we can, so this is how we can write it. At the same time, we can also say that 1 is equal to e to the power j times 2 pi. That's where we find it. Or we can say that 1 divided by square root of 2 plus j times 1 over square root of 2. What is this? Can you identify this one? What should be this number? Okay, anyone? Besmir? Andy, Gini, if we start from alphabetically from the start. So, if we look at the complex numbers, so 1 is this point here in the real domain. 1 is e to the power j times 2 pi, or 0. Then minus 1 it's e to the power j, but the angle is plus pi, okay? So if we check here, -1 is e to the power j pi. So this tells us how much will the angle change with respect to 0, okay? That's -1. I, what was I? I is a number here. So what is this? 1 over square root of 2 plus j to the power plus j, that's 1 over square root of 2.
It's e to the power j times pi over 4.
That's correct, okay, pi over 4. So we move with an angle of this much. And let's not forget also, we have an Euler identity, which states that e to the power I theta, this is equal to cosine pi over 4, cosine of 45 degrees, plus j sine pi over 4, okay? So with this little review of the complex number representation of j's that will appear in our phasors, delta phasorica, the phasor de chemica, what there, mund të themi që fusha elektrike mund të ketë këto komponente. So we have C1 plus JC2 times e to the power minus j beta z. Let's assume for a moment that the wave is moving in the positive z direction. It could be a different one for sure. But if it is like this, then the electric field has to be perpendicular to the propagation, right? So I did not write this one completely, but probably this would be best if we write like AX C1 plus J AY C2 times e to the power minus j beta z. That's good. But then this whole thing will take the cross product with H. Okay, we know that every component of the electric field will have a representative H. Okay, otherwise we would have no wave. So for this one, we can be asked to write a complete expression for the H also. So let's take this out. And we can write, let's assume, we can have the E as a function, the instantaneous expression for the electric field. This can be denoted as AX EX plus AY EY. And this would be equal to C1 times AX cosine omega t minus beta z plus AY cosine omega t minus beta z minus pi over 2. Okay, so here we have a representation of the electric field, instantaneous expression of the electric field. We notice that here, the delay, here, this cosine minus pi over 2. So we know that this whole expression, I'm going to erase this one in a second, but let me write it like this. We know that this cosine, this has come from the expression of the real part of e to the power j omega t minus beta z, okay, times e to the power minus j pi over 2, right? So this is how we pick this up. And this was at the same time, so I'm going post-analysis of, we have got this one, but we are going back in time. How did we get this? We remember from the phasor discussion, which we have started from the last semester together in the electromagnetic field theory class. But as a reminder, this is a result of a real component of this, and this would be equal to the real part of the phasor, which looks like this, e to the power minus j beta z minus j pi over 2 times e to the power j omega t. We know that when we get the instantaneous expression, the phasor, which in this case, this would be the phasor, we multiply with time propagator, which is e to the power j omega t, we take the real part. Okay, so if we do that, we get this expression. And at the same time, I can also, this also serves like a small reminder. This is the real part of j e to the power minus j beta z minus j pi divided by 2. Okay? So this is what we have for the EX and EY. Good. So this was the, we did not denote this one. Oh, this is the electric field. The question is to determine what is the magnetic field. the magnetic field is going to be equal to AX, HX, plus AY, HY. So this whole thing would have an amplitude of C1 divided by eta. Sorry, X, how can I read this one? No, this was eta, right? Yeah. This was eta, C1 divided by eta, times, then we continue like this, and we should keep in mind that at any instant, we should get a cross product between these components. We should get something along the Z, okay? And now, if the wave is moving across the Z, how can we get, so let's say, how can we get a plus Z if we take AY times what? So we have, here we have AX, this is AY, and this is AZ. If the wave propagates in this direction, AZ would be equal to minus AY cross AX, right? Because we are moving counterclockwise, and we should get here a plus. In order to do that, we put a minus sign. So what we mean here is that we may expect here minus AX times cosine omega t minus beta z minus pi over 2. So if you watch closely, these two are associated like this, okay? Phaza, the phase which is in this component of AY, it should match with the phase here, okay? And then we continue, we say plus AY times cosine omega t minus beta z. Okay? And these two are kind of in phase with this one other here. Okay? So now this is the expression for E and for electric field and the magnetic field, which would constitute a full wave. So let's do an example. So once we have this here, so given electric field in the phasor notation, which is equal to C1 minus J AX plus AY times e to the power minus J beta Z. Okay. So this is the phasor notation of a given electric field at a specific frequency. The first question is, let's find the polarization. Or we can call this one determine polarization. When I say determine the polarization, this really means find the direction of the electric field. Where is the direction of the electric field? Well, we have here AY, so it looks like we could say along the AY, but it's hard to say that because we have also a component along the AX. But this is a component along the AX. We see that there is also a phase difference between these two, right? So we have that minus J, which appears over there. And once you see this expression, you can start to contemplate, or you can start to argue on a piece of paper, okay, which one is leading which, okay? So apparently, this minus J, this is a function which is e to the power minus J pi over 2, whatever, okay? So that terms should appear over there. So the first question being this, it's something between AX and AY, but the delay might determine what we're going to deal with. But we can also, what can you say about the amplitude? Do you see what is the amplitude for the electric field along the X direction and along the Y direction? What is the amplitude for the electric field along the X direction? What can you say about this one? Any answer would be very thankful. I would be thankful.
Is it C1?
It's C1, so they're equal. So the amplitude of the electric field along the x-axis is equal to the amplitude of the electric field along the y-axis. Because this is the amplitude, it's C1, right? We don't have any constant that appears in here. So here we have that the instantaneous expression of the electric field EZT is always equal to the real part of the phasor times e to the power j omega t, right? So this is what we do, and then we continue, and here we'll get that this is the real part of AX times C1 e to the power minus j pi over 2 times e to the, so we found this j here, okay, so we entered it. So we write here AX, C1 is here, j is here, then we have here e to the power minus j beta z, and let's write separate e to the power j omega t, and we know that this is the new term that comes up, right? And probably you can see this one in the camera. I can erase this part because we tried to denote this one before movement. So this is the EX, then we continue, plus AY times C1 e to the power minus j beta z e to the power j omega t, okay? So this is the instantaneous expression of the electric field. Starting from this, given this, which is above in red, and the rest. So with hold this expression, we get the following. So this is going to be equal to, now what is the real part? Now here, if you use this component EX here, this is an expression which will be like this, e to the power j omega t minus beta z minus pi over 2, right? So this one, it is pretty obvious. And we know that the real part of this e to the power j is equal to the cosine of the same argument, of the same angle, okay? So here we have, this is going to be equal to AX times C1, let's not forget the quotient, times cosine of omega t minus beta z minus pi over 2. Okay, this is the EX. By the way, have we forgotten anything here? No. Okay. Then we have here plus AY times C1, then again cosine omega t minus beta z. Okay. So this is the instantaneous expression of the electric field. So what do we observe here? We observe two waves which are along the x and y. The amplitudes are the same, and for EX it has it's minus pi over 2. So this way that is here minus pi over 2, this makes this left hand circularly polarized. Left hand circularly polarized. And left hand circularly polarized, what we can do is that we can fix z equal to 0, and we can progress in time. So if we set here z equal to 0, and we can observe how EX and EY will be. So wait a second, this is going to be 1, or it's 1, yes. So this is, then the next question we can ask is the following. We can try to determine what is H. Find H, but the phasor, not the instantaneous expression. So this one we can try to determine from the initial phasor that we have, and this can be written as C over the eta over the intrinsic impedance times minus AX, okay, minus JAY times e to the power minus j beta z. Okay, so how could we, this is C1. So whatever the amplitude of the electric field is, we define by the intrinsic impedance, and then we try to observe the corresponding components. So here we have, what should we have? We should have that this component AX when we take the cross product with this AY, we should get AZ. How can we do it? Let's see what we obtain from here. This is minus J AX, minus J AX. We take the cross product of this with minus J AY, right? So these are like this. So this is minus minus is plus. And but wait a second, is this correct? Minus minus is plus. This could be even wrong. Let me see. So E cross J, we should get a propagation along the plus Z. Then we should get here, this is plus, minus, this is minus AZ, right? Then this should be plus, I believe. This is plus, plus. Then similarly, in order to get plus AZ, we should get from the electric field, we get AY cross product with minus AX. This is equal to AZ. This should be plus, okay. So we get the propagation along the AZ only if we respect these values for the magnetic field phasor. Now another question that we could consider is the following. So this is just the wave itself, but we have not provided much information. Let's assume that this is an antenna, this signal, which has this electric field and this magnetic field. This is an antenna at a distance around 1,000 kilometers, and this transmits 40 kilowatt power transmission. So this transmits such a high power at a specific frequency, which is equal to 137.5 megahertz. Okay, at this specific frequency, and let's try to determine what is the beta, what is the phase constant. Okay, so how can we define the beta? Now, if we can write this one in different ways. This is equivalent to the following. These two are exactly the same expressions, so not much is changing. We haven't said anything about the relative permittivity or relative permeability, so we keep them like this. And then what would be omega? Omega at this time, so we know that this is 1 over c. This would be 2 pi f, where frequency it would be 137.5 times 10 to the power 6 divided by 3 times 10 to the power 8. So the beta then would be equal to something around, so this is 136, this is 10 to the power 2, times 10 to the power 6, we get 10 to the power 8. So they cancel out, so it looks like it's going to be a number around 10 to the power 0. And here the exact value is 2.9, and the unit is radian per meter. So this is the phase constant. Then another important parameter that we may try to determine is what is the amplitude of E, which is the following. What is C1? So if we're asked about what is C1, how can we determine it? We have to find a relationship with this power here. Okay? So if we have 40 kilowatt of power transmitted, we have to figure out. So this is total power transmission, okay? We don't have here any watt per meter square. So here we can say what is the time average power density. Time average power density is a quantity which has units, let's write here equivalent, which is watt per meter square, okay? So we want to find this number, right? But let's first determine this. And this would be equal to the total power which is transmitted, 40 kilowatt, and 40 kilowatt is 40 times 10 to the power 3, divided by the total area where this energy is being distributed. Now, antenna, let's assume that it has an equally spaced power distribution as a function of the angle, so there is an equivalency, all the angles are equivalent. then we would have to divide this by 4 pi r squared. The radius is 1,000 kilometers. 1,000 kilometers, this makes it 10 to the power 6 squared. 10 to the power 6 squared. And this would be equal to, so we did not know this before, but based on this total power transmission, we get a number of approximately, let me think for a moment, we should get here. This is 10 to the power 3. This is 4, 10 to the power 3 times 10. This would be 4. This 4 can cancel out this one, so we can take this out completely. The 4 is gone. This is 10 to the power 4 divided by pi times 10 to the power 12. Okay, this makes this 1 over 10 to the power 8 times pi. So this is the time average power density, and this would be equal to C1 squared divided by 2 eta. So this is equal to C1 squared divided by 2 eta. But now, and then from this expression, the C1 would be equal to 2 times 377 divided by pi times 10 to the power 8 all square root. Okay? So in this, then for C, we found something like 1.5 millivolt per meter. C1 is 1.5 millivolt per meter. Okay. So this is all the, this is the amplitude of the electric field for this system, or for this antenna, which produces this much power at a specific distance. 1,000 kilometers. What is 1,000 kilometer? We know that the radius of Earth is like 6,000 kilometers. Okay, so if you drive from here to Spain, it's like 2,000 kilometers. But if you stop somewhere in France, you get 1,000 kilometers. So that's how far it is. So if you have an antenna, you send a signal from Albania somewhere in France. France is huge, actually, so it's hard to say somewhere in France. It should be something like more precise, because France is a large country, but somewhere over there, you can pick up these. So if we have an antenna with this amplitude, okay, at this distance, we can produce this much energy, but yeah. And yes. Okay. Do you have any question? Now we did circular polarization, and after circular polarization, we can define also elliptical polarization. But this one we're going to discuss in detail in the next session. So next topic, it will be elliptical polarization. Now, elliptical polarization is going to be very similar to circular polarization, but the conditions will be the following. It's going to be either Ex is different from Ey, okay, or phase is different from pi over 2. Okay, so phase difference, we notice that in circular polarization, we have that the amplitudes are the same, and phase angle is pi over 2. With elliptical, we have this new configuration. Now, do we have no configuration? This either one of these two combinations. So non-equal amplitudes along the x and y, and or different phase difference other than pi over 2. Do you have any question for so far? Anything which is not clear? Okay, so if this is all, then we can